Hi everyone. In this video, we'll continue our discussion of sequences of functions, and in particular, we'll continue looking at uniform convergence and some of the consequences of having a series of functions that converges uniformly. This is not a conversation that we will finish in this video. We will continue it in the next, but we want to begin today by revisiting uniform convergence, looking at an alternative characterization, and looking at one of the first major consequences. So to begin, let's remind ourselves of the definition of uniform convergence. So a sequence of functions f sub n converges uniformly to a function f on a set A if and only if, for any epsilon greater than 0, there's a natural number capital N, so that whenever little n is greater than capital N, then this difference, the absolute value of f sub n of x minus f of x, is less than epsilon for every x. So remember here that the key differentiator between uniform convergence and pointwise convergence is that this choice of n here is independent of x. I can pick a single n which works for every x. With pointwise convergence, my capital N was allowed to depend on x. And so therefore I would first fix an x, then choose a capital N that worked for that particular x, and show that this inequality was satisfied only for that particular x. But now for uniform convergence, I want to be able to find one capital N that works for every value of x in my set A. So we looked at in the previous video some examples. Let's begin by looking at another. So consider the sequence of functions f sub n of x is equal to x divided by 1 plus nx squared on the closed interval 0, 1. Now, this is a sequence of functions, unlike, say, x to the n, which I think is a little harder to conceptualize. I will include in the resources to go along with this video a Desmos graph to allow you to explore some of these. But we can also think about this from a purely algebraic analytic perspective to try and determine whether this sequence of functions converges pointwise and or uniformly. So in order to begin, it's always helpful if I'm going to prove something is converging, I need to have some candidate for the limit. And in fact, when it comes to sequences of functions, often what this means is we look at it pointwise. So we show that there's pointwise convergence. Then we try to show maybe that there is or is not then uniform convergence as well. So let's think first about what the pointwise limit of this sequence of functions may be. So let's fix an x in A. Okay. Now, if I fix an x in A, then what is the limit as n goes to infinity of f sub n of x, right? If x is fixed, then this is just a sequence of real numbers. And this is the limit as n goes to infinity of x divided by 1 plus nx squared. And I should be, I'll be even more specific. I said A here. In this case, our A is 0, 1. Okay. Well, we could start by testing some specific things. So let's say X happened to be the fixed value 0. If this was the fixed value 0, then this would just be the limit as n goes to infinity of 0. Okay, so that limit would be 0. If X happened to be 1, then this would be 1 over 1 plus n. As n goes to infinity, that would go to 0. Okay? And in fact, for any fixed x value, the top will be fixed. Here I just have a 1. The x squared will be some fixed value, and now n is going to go off to infinity. So the numerator is fixed. The bottom is going to go to positive infinity. We have x squared here, so that's always going to be non-negative. So in fact, this limit will be 0 for any fixed value of x between 0 and 1. Okay. So what does this tell me? This tells me that this sequence of functions, f sub n, converges to the 0 function pointwise on the interval 0, 1. All right, so I now have the pointwise limit. Now the question is, does it only converge pointwise or does it also converge uniformly? So we mentioned in the previous video that uniform convergence implies pointwise convergence, right? But the converse is not true. So you can think of sort of convergence as sort of having different levels of convergence where the base level is pointwise convergence. And then above that, you have uniform convergence. Okay. So, and I should mention that there are other types of convergence. And so the pointwise isn't necessarily the ground level. There are other forms of convergence which may be even weaker in certain senses than pointwise convergence. But we can think of pointwise convergence when we're talking about pointwise versus uniform. Pointwise is the lower level. So now we know this converges pointwise. We want to see if it also converges uniformly or not. Okay. Now, but just think for a second, right? As I think about this calculation, normally if I was going to do like an epsilon delta style proof of this limit, right, I would want to look at f sub n of x minus f of x, right? And I'd want to show that in absolute values, I could always make that less than epsilon. And I would take this and I would try to solve it for little n to find my capital N. So if I do this here, right, so I just get x over 1 plus nx squared minus the limit function, I think is 0. Okay, and now x is between 0 and 1, so it's non-negative. This is non-negative. All the absolute values can come off. And I get this. Okay. And so I could look at this and I could say, okay, well, I need to solve this for n. Okay, so if I solve this for little n, and I'm gonna skip some steps here, but if I solve this for little n, I will get x minus epsilon over x squared epsilon. So I almost get like this is my capital N, or it's roughly my capital N, right? But the first problem I sort of see is that this capital N depends on x. So if I want uniform convergence, this is where I have to be careful. If I want uniform convergence, I want to find a capital N that is independent of x. Here, I have found a capital N that depends on x, but that doesn't mean that it's not possible to find a capital N that is independent of x. So just because in this sort of first pass through, I find a capital N that happens to depend on x, that doesn't mean there's not a way to find one that is independent of x. Okay, and in fact, we can in this situation. Let's think about how we might do that. Well, if I look at this. Okay, this is really just my function again, right? So what I might want to do is try to find an upper bound for this function that is independent of x, right? And then I will make sure that my capital N is chosen so that this thing is less than epsilon, which will make this less than epsilon. Now the question is, how do I find the thing that's in here? Now, I could just sort of play around with some x stuff, right? So I could look at this and I could say, what's the smallest that what's the smallest that x could ever be, right? And well, that's 0. And if I just put 0 there, then things sort of disappear. Okay, so maybe that's not good. I could look at the bottom and say, well, I make the bottom as small as possible. If I make the bottom as small as possible, well, that happens when x is equal to 0, but that makes the n disappear. So that's not particularly good. We sort of say, well, okay, maybe that's not the best plan. Let's actually look at this function and let's see if we can find the maximum value of that function. Okay. So let's look at this and ask ourselves, what is the maximum value of this function? Okay. Well, that's just a little calculus problem, right? So I'm gonna come back here because this is really what I'm working on. So let me get rid of this. So now if I want to think about uniform convergence, let's ask ourselves, what is the maximum of this? Okay, well, to find the maximum, I can find where the maximum occurs by finding the critical values. So I need to take a derivative of this function with respect to x. I'm going to need to use the quotient rule. So low d high minus high d low all over low low. Okay, there's the derivative. I can clean this up a little bit. So let's see, I have a 1, and then I have a plus nx squared and a minus 2 nx squared. So I get a minus nx squared over 1 plus nx squared. Now to find the critical values, I want to find where this is 0 for what values of x. Well, the only way this fraction can be 0 is if the numerator is 0, and that will happen when x is equal to the square root of 1 over n. Now, that is the x value at which the maximum will occur. Actually, technically, that's just a critical point, right? I might need to do something like a first derivative test to verify that this is in fact a maximum, but it is. But what I actually need is the maximum value. This is the location, the x value where the maximum value occurs, but I need the actual maximum value. So I'm going to go back and plug this x value into my original function. Okay. So if I plug this in, oh, sorry. So plug this into my original function here. So this will be square root of 1 over n divided by 1 plus n times the square root of 1 over n squared. Okay. This quantity in the denominator just becomes a 1. So 1 plus 1 is 2. So I'll get a 1/2 square root of 1 over n. And that is my maximum value, right? So notice, if I look at this, now what I could come down here and say is, okay, why don't I know that this, on the interval 0, 1, and actually this is true on all of R, but certainly on 0, 1, the maximum value of this function is this. And let me just make that less than epsilon. Okay. Now, if I can do that, right? So I could come over here and I could choose. So what would I need? I would take this to make this happen. I would want the square root of 1 over n to be less than 2 epsilon. Then I'd square that. So I'd want 1 over n to be less than 4 epsilon squared. And that would give me n is greater than 1 over 4 epsilon squared. All right. So now I could come over here and I could say, okay, this actually does converge uniformly, and here's how I'm going to prove it. Okay. So we're going to start by, again, just noting that the maximum value of x over 1 plus nx squared on 0, 1 is 1/2 square root of 1 over n. And so I'm going to choose a natural number n so that this n is greater than this 1 over 4 epsilon squared. Hence, when little n is greater than capital N, the absolute value of f sub n of x minus f of x, well, this is just going to end up being x over 1 plus n x squared. So that's this term minus 0 in absolute values, but this is always positive, so we drop the absolute values. All right, now I can replace this I'm going to put something smaller in the denominator that'll make this bigger. Okay. The maximum of this function, right, well, actually, sorry, let's do this first. So the maximum of this function is always less than or equal to 1 over 2 square root of 1 over n. Now I'll put something bigger in the denominator, sorry, smaller in the denominator here, which will make this bigger. Now I'll put something even smaller. Okay. And if you calculate that out, you just get epsilon. All right. So this worked, but it sort of required doing some tricky analysis over here to get the correct choice of capital N that was actually independent of X. Okay. And one of the things that I want to point out here is that what we really did, yes, this is f sub n of x, but I can also think of this as being, right, this is also this quantity. In this particular case, f sub n of x is equal to the absolute value of f sub n of x minus f of x. So if I think of this as being sort of its own quantity, capital, if I think of, me wait, because I don't want to use that yet. If I think of this as being its own quantity, what I really was trying to do was to find this, where this quantity right here was just the supremum of this thing. Okay. So the important thing down here was actually to be able to find this value, m sub n, which was like the supremum of f sub n of x minus f of x. And given that I could find that value, and given the fact that like this goes to 0 as n goes to infinity, if it didn't, I wouldn't be able to solve for capital or for little n in this way. So given both of those things, I was able to make this proof work. So what we actually want to do, this is a perfectly good standalone proof, but we actually want to generalize this idea to come up with an alternative sort of characterization of uniformly convergent series. One which really sort of takes this idea and builds out a theory around that. All right. So what we actually get is a theorem. This is sometimes called the test for uniform convergence, but it's also really just an alternative characterization of uniform convergence. So suppose f sub n converges pointwise to a function f on a set A. And now here I want to set this capital M sub n to be the supremum over all x in A of f sub n of x minus f of x. So the idea is this is the thing you want to make less than epsilon. So figure out what the biggest this difference could possibly be by looking at every x in your set A, right? So this supremum over all x in A, that's the least upper bound of this quantity, right? Then if I can make that less than epsilon, then I'm good. Well, how would I know I can make this less than epsilon? I would know I could make this less than epsilon if this thing converges to 0 as n goes to infinity. So what this test says is, so take this quantity m sub n, the sequence f sub n will converge to f uniformly on A if and only if this sequence capital M sub n converges to 0. So again, this is if and only if. It really means you could exchange this with the definition of uniform convergence, and it would work exactly the same, right? So if f sub n converges uniformly to f, then this quantity must go to 0. But also, if this quantity goes to 0, then f sub n must converge uniformly. Okay. Now, again, because it's if and only if, we can also negate things. So if this sequence, if m sub n does not go to 0, then f sub n does not converge uniformly to f. Okay, so we can go back, for example, and we'll look at a further example in a second, but go back to that sequence of functions, f sub n of x is equal to x to the n on 0, 1. We showed that this converged pointwise to the function which was 0 if x was between 0 and 1, including 0 but not 1, and 1 if x was equal to 1. Well, if I look at that in the context of this theorem, what is capital M sub n? That would be the supremum over all x in 0, 1 of f sub n of x minus f of x. Now, if I just to sketch a picture here to help remind ourselves. So, I had this sequence of functions. They sort of looked like this. Okay. And then my limit function, right, is 0 right up until we get to 1 and then 1. So I want to analyze this difference over the entire interval 0, 1. So at 0, the difference is always 0. At 1, the difference is always 0. In between, right, for different values of x, we get different things, but we want to know what the supremum is. Well, I can always go sufficiently close to x is equal to 1 and get a difference that's as big as I would like, right? So if I wanted to see if there was a difference, well, hold on, I should be careful. I can't get one as big as I would like, but I can get it like as close to 1 as I would like. So there's one that's like up to a half, but I could go over a little further, and maybe there I'm at 3/4, right? And I go over even a little bit more and a little bit more and a little bit more, and I'm never quite getting to 1, but the difference between my function value and the value of the limit function is as close to 1 as I would like. Never actually equal to 1, but as close to 1 as I would like. So this supremum is actually 1 for every natural number n. Okay. So then you look at the limit as n goes to infinity of the m sub n's. Well, that's just, those are constant. Those are all 1. So this limit is 1. Since this limit is not 0, m sub n does not converge to 0. M sub n here converges to 1. So this does not converge uniformly. Okay. So again, this is helpful in a lot of ways. It's helpful both for proving that things do converge uniformly, but also for proving that things do not converge uniformly. That's the real power of these sort of if and only if theorems. All right. Again, looking at one more example, and again, one where we'll actually use this to prove something doesn't converge uniformly. If we go back to this example, which we saw earlier, these are those marching triangles. So the triangle is, the peak of the triangle is at 1 over 2n, and it has height n, right? So the peak of the triangle is moving closer and closer to 0. However, the peak of the triangle is also moving up each time. So we showed previously that this sequence of functions converges to the 0 function pointwise. Okay. So we could ask ourselves, does it converge to 0 uniformly? Well, what would those m sub n values be? It'd be the supremum over all x. Again, we're working on 0, 1 here, of f sub n of x minus, in this case, 0. Okay. So this is really just the supremum over all x in 0, 1 of just f of x, because f of x is always non-negative, so I can drop the absolute values. Okay. Well, the supremum of this function is going to occur at the peak of that triangle, right? And at the peak of that triangle, this has value n, right? So the peak of the triangle occurs at 1 over 2n. If you plug in 1 over 2n, right, you'll get 2's in the denominator that cancel, and n squared over n is n. So this is just n. So here, that m sub n here actually is varying with n. But if I look at the limit as n goes to infinity of m sub n, this will actually diverge to infinity. Most importantly, it's not zero. And since it's not zero, that test for uniform convergence implies that f sub n does not converge, uniformly. All right. So we have this newer type of convergence. Okay, so we have this notion of uniform convergence, and a perfectly reasonable question to ask is sort of who cares, right? Why do we care? Why should we care about having a different type of convergence here? Now on the one hand, you could say, well, it's mathematically interesting. It's just a different definition that we can play around and do things with. But it also turns out that uniform convergence is going to be a nicer type of convergence in that certain characteristics from the sequence can be inherited by the limit if the sequence converges uniformly. So if we go back, for example, to that sequence of functions x to the n on the interval 0, 1, those are all nice and continuous functions. Every function in the sequence is continuous. However, the limit function is not continuous. Why? Because the convergence of the sequence was not nice enough to preserve that property that each of the sequence functions have and pass it on to the limit function. However, what we're going to see is that uniform convergence will allow us to say, in some cases, that, oh, your sequence of functions has property x. The limit function will also have property x if it converges uniformly. So let's look at our first example of that. If a sequence of functions, each of which is continuous, converges uniformly on a set, then the limit function is also continuous on that set. So the idea is if you have a sequence of functions and all of the functions in that sequence are continuous, and if that sequence of functions is converging uniformly to something, then the limit function is continuous on that set. So as we've seen, this can fail when the convergence is only pointwise, right? So again, that sequence x to the n converges pointwise, but not uniformly. And it's a sequence of continuous functions, but the limit is not continuous. Okay. It's also worth noting that it is entirely possible, this doesn't preclude the possibility that you have a sequence of discontinuous functions that converge to a continuous function. So if you were to take, for example, one example would be if you take the sequence of functions f sub n of x is, say, 1 over n when okay. So you have this sequence of functions where on the interval from 0 to 1 over n, these have height 1 over n. And then there's 0 relative to 1. So what's happening this point as n gets larger is moving to the left. Also, these are getting smaller and smaller and smaller. These are all discontinuous at 1 over n, but they converge uniformly to 0, to the 0 function. So you can have a uniformly convergent sequence of discontinuous functions that converges to a continuous limit. But what this says is if your sequence of functions is continuous, then and it converges uniformly, then the limit function must also be continuous. Okay. So let's first, before we get into the proof, we first sort of just want to sketch out and think through how we might prove something like this. So the first question is to ask yourself, okay, what is it we would actually need to show? So we're trying to show that the limit function, we'll just call it f, is continuous. At the end of the day, this is a proof about continuity of a function. Okay, so what do we want to show? We want to show that for every epsilon greater than 0, there exists a delta such that whenever x is in the domain of our function, but in this case, the domain of the function is going to be this set that it's converging on. We've been calling that A. So such that when x is in A and when x minus, okay, now this is where I got to remember, how do I prove continuity on a set? I prove that it's continuous at each point in the set. So let's just call that point A. Okay. So whenever x is in my set A and the distance between x and little a is less than delta, we have, well, let's see, I'm going to want f of x minus f of a. I'm going to want to make that less than epsilon, right? So that ultimately, at the end of the day, right, I've got to explain how for every epsilon, I'm going to choose a delta so that this is true. All right. Well, let's try to come up with a little bit of a game plan. Okay. I want to be able to say something about this difference. But right now, that's a little bit hard because I don't know anything about the limit function, right? All I know is I have this sequence of functions. Each of the functions in the sequence is continuous, and that sequence is converging uniformly. But those are all sort of, at the end of the day, they're sort of properties about either the sequence of functions, namely that those are all continuous, or about how the sequence of functions relates to the limit function, right? That the convergence is uniform. So somehow what I need to do is I need to re-express this and be able to relate it back to like at least one of the functions in the sequence of functions. So let me imagine, and we'll figure out exactly how we're going to pick but let me just pick a function out of the sequence. Let's call it f sub m. Okay. So what I could do is I could look at this and I could say, well, okay, I don't know anything about f really, but I know about how f relates to f sub m. So maybe instead of looking at this difference, maybe I want to introduce like an f sub m of x, right? Because now I might be able to say something about this difference because this is maybe something about how f sub m relates to f, how the sequence function relates to the limit function. Well, I can't change the value though, so if I subtract that, I've got to add this. Okay. Now, same thing over here. I don't know anything about this, so I probably want to introduce an f sub m of a. And so what I'm going to do is put an f sub m of a there, and an f sub m of a here. And I'll still have my minus f of a. And so what we see, right, is I sort of have these three blocks now, right? So I have this block, and this block. And let me just go ahead and I'm going to apply the triangle inequality to keep all these blocks together. Now, I look at these and I say, okay, if I could get, say, each of these less than epsilon over 3, so this is less than epsilon over 3, this is less than epsilon over 3, this is less than epsilon over 3, then I'd have this whole thing is less than epsilon, which is what I want. Okay, well, how might I be able to control these terms? Okay, now, if I look at the first and the last terms, what are these? These are really things about how f sub m relates to f, right? The inputs are fixed, right, and are the same, right? So this is, how does f sub m of x relate to f of x? How does f sub m of a relate to f of a? Well, probably here, I should be able to use the uniform convergence, right? This is something about how close, right? If this sequence of functions is converging uniformly, I should be able to get this difference to be as small as I would like. So hopefully I can use uniform convergence to control those. Now, what about this middle one? Now, this middle piece, this is really only about the function f sub m, okay, which is one of my sequence functions. And what do I know about those? I know they're continuous. And I look at this and I say, yeah, okay, this looks like if this function is continuous, right, I should be able to choose a delta so that whenever these conditions are satisfied, I can make this difference as small as I'd like. So I'd like to control this by the continuity of f sub m at a. So as I start a game plan, and again, this is not the proof yet. We'll wipe the board, we'll flip over to a blank slate, and we'll write the proof out in a minute. But the idea is that I should be able to use the continuity of f sub m and this uniform convergence to control all of these terms. Now, the one thing I do have to be careful of, I still haven't, like, how do I choose this f sub m? Well, the idea is going to be that I have to pick using the uniform convergence first. I need to say I'm going to go far enough out in my sequence of functions that these differences are not very large. So choose m to be a function, one of the functions that's far enough out in my sequence. It can be any one of those functions, but choose one of them that's far enough out in the sequence. Now my m is fixed. And now that my m is fixed, I can control this difference, right, using the continuity of that specific f sub m. Okay. So that's going to be the idea of the proof, that I need to control each of these terms. And then at the end of the day, I'll be able to wrap it all up and say, okay, well, then this difference, which is less than or equal to this difference plus this difference plus this difference, each of these I can make smaller than epsilon over 3. So this whole thing is less than epsilon. Okay. So we've got a game plan. As with all game plans, it's a plan. We may have to make some adjustments once we get in the middle of things, but hopefully this is a pretty good idea and a pretty good plan of attack to prove this theorem. All right. So let's give ourselves plenty of room. All right. So let's start our proof. So what are we going to want to do? So we want to prove that this function is continuous at any arbitrary a. Okay, so we're going to start by fixing a in our set A and letting epsilon greater than 0 be given. All right. Now, remember, thing number one, we got to choose that function f sub m using the uniform convergence. Okay. So since f sub n, the sequence of functions, converges uniformly to f, there exists a natural number, capital N, such that f sub n of x minus f of x is less than, I can make this as small as I want. I want to do it less than epsilon over 3 here. So this is less than epsilon over 3 for all little n greater than, for all x, and for all little n, for all x in A, and little n greater than capital N. Okay, so this is just using the uniform convergence of the sequence of functions f sub n to f on the set A. Okay, well, then just choose m to be greater than n. Basically, choose m to be one of these functions for which this is true. Okay, it's true for all little n greater than capital N, so just choose some one. Okay. Okay. So now, since f sub m, okay, so now I'm looking at the specific function f sub m. Since f sub m is continuous on A, there exists a delta greater than 0 such that when x is in A and the absolute value of x minus A is less than delta, f sub m of x minus f sub m of A can be made as small as I'd like. I want to make that less than epsilon over 3. Okay. So first I use the uniform convergence of the sequence of functions to get it so that I can find a capital N so that all my functions beyond that are within epsilon over 3 of my limit function for all their x values. And then I just pick one of those functions that this works for. Now I say, well, hey, that function's also continuous. Why? Because all the functions in the sequence were continuous. Okay. And since this is continuous, then I can find a delta such that whenever x minus a is less than delta, then f sub m of x minus f sub m of a can be as small as I'd like. I want that smaller than epsilon over 3. All right. So hence, when x is in A and x minus a is less than delta, now I want to look at that quantity f of x minus f of a. Okay, and I'm just going to repeat my game plan, right? So this is going to be less than or equal to, I'm going to add and subtract all those terms and triangle inequality. So this is going to be f sub x minus f sub m of x in absolute values plus absolute value of f sub m of x minus f sub m of a plus the absolute value of f sub m of a minus f sub m, minus f of a. Now, by my choice of m, right, this and this are both less than epsilon over 3. Now, you might say, Quinn, this is the only, these two, okay, they're flipped around, you got to, but okay, I get that. But here you have a and not x. X is just a dummy variable. This holds for every x in the set A. A is a value in the set A. So this inequality holds just as well for this difference as it does for this one. So these are both less than epsilon over 3 by our choice of capital M. So it's by our choice of lowercase m. So we chose our function f sub m, we chose our m, so that these would both be strictly less than epsilon over 3. Now this middle term, why is it less than epsilon over 3? It's less than epsilon over 3 because x is in A and x minus A is less than delta. And we chose our delta that way using the continuity of f sub m. Okay. So again, just like our game plan, these two are controlled by the uniform convergence. This is controlled by the continuity of f sub m. So each of these is less than epsilon over 3. The whole difference must be strictly less than epsilon. I should write equals here because it equals the previous line, but it's still less than that. Okay, so what do we conclude? So f is continuous for all A in A, right? I fixed an arbitrary element of A, never used anything specific about it, so this works for all A and A. So F is in fact continuous on the entire set A. Now, I do want to point out that, right, again, this doesn't work if you only have pointwise convergence, but I think it's tempting to ask sort of, well, why not, right? And the reason really is that you need the uniform convergence so that you can choose a single function where both of these values, right, regardless of what x is, I know that this difference will be less than epsilon over 3. I need the same m to get my function, my f sub m of x and my f of x need to be within epsilon over 3 of each other for every x. So I really have to have the uniform convergence here. If I don't, I can't control these terms in the way that I need to. Okay. So we are going to conclude this video here. But again, we're starting to see that uniform convergence, it preserves some nice properties of the sequence function and carries them over to the limit function. And so you might wonder, okay, we've seen that with continuity. Are there other things? What about the values of integrals? What about the values of derivatives? Does it preserve those things? And the answer is, in short, that for integrals, it will pretty much preserve the integral. So if you have a bunch of functions, a sequence of functions, and all of them have the same integral value, then the limit function will have the same one. But for derivatives, that won't quite work. Okay, so we're going to see that uniform convergence does preserve some things, but not all things. That, of course, if you go further in analysis, you'll learn of many other types of convergence which preserve different types of things. But for our purposes, we're going to really just examine what happens with uniform convergence and see how far we can push that until things break down.